Hello everyone. In the 7th lecture of chemical equilibrium, a thermodynamic approach, our topic of discussion is equilibrium constant and standard Gibbs free energy change. So we have the reaction isotherm. Delta G equals to minus RT ln Ka plus RT ln sum over I ln AI to the power nu I in terms of activity, which is actually we are recalling equation number A from our previous lectures. If the reaction is carried out in such a condition that every reactants and products be maintained at unit activity, that means these values of A activities should be written as 1 only. That means unit activity. That is, all the reactants and products are at standard state. That means unit activity is actually the standard state. And definitely at standard state we should write AI to the power nu I equals to 1, because whatever be the power, if it is base 1, then the result is always 1. Okay, so in that case, standard state, this term becomes 0 because ln 1 is always 0, isn't it? This would be reduced to ln 1 if A is equal to 1. Okay, and hence its summation is also 0. And if unit activity means standard free energy, standard state, that means free energy would also be standard. That means delta G can also be written as delta G 0. So if we put A equals to 1, then we have to write delta G equals to 0. In that case, delta Z 0 would be equal to minus RT ln Ka. So this is the result from equation A that we have here, like minus RT ln Ka equals to delta G 0. Okay, so we have got a new term which is standard Gibbs free energy change and written as delta G 0. So we have equation A, B, C, D, E, isn't it? So equation A has the special form delta Z 0 minus RT ln Ka. This is not special form, this is a reduced form. Okay, in terms of mole fraction, it is Kx, concentration Kc, fugacity Kf, and pressure Kp. So we can now put delta Z 0 instead of all these terms in equation A, B, C, D, and E. This way we get these equations. Equation A may now be written as A1 and up to equation E, E1. Okay, so the expressions are delta Z equals to delta Z 0 plus RT summation ln AI to the power nu I, and similarly this one delta Z 0 plus RT summation ln Xi to the power nu I, delta G equals to delta G 0 plus RT summation ln Ci to the power nu I, this one Fi to the power nu I, and this one Pi to the power nu I. Activity, mole fraction, concentration, fugacity, and partial pressure. Okay, these are about the expressions of standard free energy change. Okay, delta G0 is standard free energy, whereas delta G0 is standard free energy change, and all these delta G0s have their own corresponding values. Okay, so for a same reaction, these two delta G0 have different values, and this is one important question also. Okay, because this one you are writing in terms of activity, whereas this one you are writing in terms of mole fraction. This one has the expression minus RT ln Ka, whereas this one has the expression minus RT ln Kx. So all these 5 delta G0, although they look same, but they have different values of their own. Okay, now this expression of equilibrium constant with respect to other thermodynamic parameters such as entropy and enthalpy. Okay, one more little thing. So we have already the value of delta Z0 minus RT ln K in terms of activity, or rearranging this equation we get ln K equals to minus delta Z0 by RT, and if you eliminate this logarithmic term, then it would go to the exponential power. So we get Ka equals to exponential minus delta Z0 by RT. So this is also very important expression. Okay, and we know from thermodynamics delta Z0 equal to delta H0 plus minus T delta S0. So instead of delta Z0, we can also put this value, resulting in this expression having two exponential terms. One is exponential minus delta H0 by RT into exponential delta S0 by RT. Okay. Now, if delta H0 is more negative, okay, then Ka has a greater value, and if delta S0 is more positive, then also Ka has greater value. So in order to get a great extent in the forward direction reaction, then we have to either have more negative delta H0 value or more positive delta S0 value, and vice versa. That means if delta H0 is less negative or delta S0 is less positive, in those cases this Ka value would be lesser. That means the reaction would not move towards the forward direction. Okay, the production would be lesser. So these are the conclusion that can be drawn from this. Okay, so in what condition delta H0 can be negative? If it is an exothermic reaction. Okay, in what condition delta S can be more positive? If delta nu, that means the coefficient difference, is more positive. That means we are producing A plus B equal to C plus D, so the number of molecules in the production site C plus D should be greater than number of molecules in the reactant site. Okay, or the volume change should be positive after the reaction. So that's all for this lecture. Thank you. Have a nice day.